In this video I'll be taking some more problems from the chapter flow through pipes. So this problem states that the head loss for a laminar incompressible flow through a horizontal circular pipe is H1. Pipe length and fluid remaining the same. Okay, pipe length is same and the fluid remains the same if the average flow velocity doubles and the pipe diameter reduces to half its previous value. The flow velocity doubles and the pipe diameter reduces to half its previous value. The head loss is H2. So let us assume in the first case the average velocity be V1. So in the second case the average velocity is twice of V1, and if in first case D1 is the diameter, so in second case it will be D1 by 2. Okay, let's assume this. So now we know that decrease in pressure for laminar flow, okay, it's been given that it's a laminar flow through a horizontal circular pipe, through a horizontal circular pipe is equal to delta P is equal to 32 mu VL by D square. Great. Now if we divide delta P by rho G, what we get? We get head loss. Okay, so this will be equal to 32 mu VL by rho G D square. Great. Now this is constant, mu is constant. Why? Because it has been given the fluid remains the same. Nice. Pipe length remains the same, rho G remains the same. So can I say that head loss is proportional to V by D square? Okay, that implies H old. I mean in the first case K V by D square, where K is any constant. Okay, I have assumed it. So it will be K into V by D square. Okay, and H new, if I replace V with 2V, because it has been said that the average flow velocity doubles. Okay, so K into 2V by D square. D is halved, so D by 2 whole square. So can I say that H new is equal to 8 into KV by D square. Okay, so this is what, this is H old. So that implies head loss in the second case will be 8 times the head loss in the first case. And what we have to find, do check whether we have to find H2 by H1 or H1 by H2. Okay, do not commit this silly error. So we have to find H2 by H1. So the answer will be C. And also the options are greater than 1, greater than or equal to 1. So the options also say that you have to find H2 by H1. Okay, so the option will be C. I have solved the same question in the previous video also, the question based on the same concept. 3 parallel pipes connected at the two ends have flow rates Q1, Q2 and Q3. Keyword is there are 3 parallel pipes. Okay, and the corresponding frictional head losses are HL1, HL2 and HL3 respectively. The correct expressions for total flow rate Q and frictional head loss across the two ends are. Okay, let me draw a rough diagram for this. This can be the case, we can say that. Yeah, this can the case. Okay, so this is Q, this will be Q1, the flow rate going here will be Q2 in the second pipe, and in the third pipe it will be Q3. From the figure it is clearly shown that Q is equal to Q1 plus Q2 plus Q3. And in parallel pipe combination, we know that HL1 is equal to HL2 is equal to HL3. That is, the head loss in all these three pipes will be equal. Similarly, I'll tell you the case of series combination also. Series connection, sorry. Series connection. Okay, so in series connection, let this be the rough diagram. This is one pipe, this is two pipe, second pipe, this is again third pipe. So whatever flow rate is passing through one pipe will be passing through second pipe and will be passing through third pipe. So here Q will be, I mean Q1 will be equal to Q2 will be equal to Q3, and the total head loss in this case, however, will be HL1 plus HL2 plus HL3, where HL1, HL2 and HL3 are the frictional head losses in the pipe 1, 2 and 3 respectively. So this is the series connection case. Okay. Next question. Water, the density is given as 1000 kilogram per meter cube. 1000 kilogram per meter cube at ambient temperature flows through a horizontal pipe. The pipe is horizontal of uniform cross section area. The cross section area is uniform at the rate of 1 kilogram per second. This is mass flow rate, m dot. Okay, if the pressure drop across the pipe is 100 kilopascal, the pressure drop across the pipe is given as 100 kilopascal. The minimum power required to pump the water across the pipe is, okay, so m dot is 1 kilogram per second. This is suppose the horizontal pipe. Okay, this is m dot. Rho is 1000 kilogram per meter cube, and the pressure drop across the pipe is 100 kilopascal. Okay, so can I say that minimum power required to pump the water across this pipe will be equal to the minimum power required to maintain the flow against head loss? Okay, and head loss will be equal to delta P by rho g. This we know that. Delta P is 100 kilopascal, so that will be in Pascal. Okay, try to work in SI units. I've told this in earlier videos also. 10 raised to power 3 into G is 9.81 meter per second square. Rho is given as 1000 kilogram per meter cube. Nice. Now power is equal to rho G Q HL. Okay, here H will be head loss. Okay, because this is the minimum power required to maintain the flow against the head loss. So power is equal to rho G Q HL, and rho into Q, what is this? This is m dot, mass flow rate. Mass flow rate is rho AV, where AV is Q, so that is m dot is equal to rho Q. Okay, and m dot is 1 kilogram per second, so 1 into G is 9.81 into this head loss, that is 100 into 10 raised to power 3 upon 10 raised to power 3 into 9.81. So that will be watt, that is 100 watt. Before filling the answer, check in which units you have to fill the answer. In watts. We have got the answer in watts, so the answer will be 100. Simple question, and I mean scoring question from flow through pipes. It is an important topic and a scoring one also. Okay, important topic. Next question, let's see the next question. So the next question says that consider steady flow of an incompressible fluid. Steady flow is given, incompressible fluid is given through two long and straight pipes of diameter D1 and D2 arranged in series. Okay, so there are two pipes of diameter D1 and D2 and they are arranged in series. Okay, so let this be D1. Okay, the pipe with the diameter D1, let this be D2, this is D2, this is D1. Okay, both pipes are of equal length, the length is equal, L is same, and the flow is turbulent. Now the flow is given that the flow is turbulent, okay, in both the pipes. The friction factor for turbulent flow is also given. The relation is also given for the friction factor. Okay, so you have to use this relation where K and N are known positive constants and Re is Reynolds number. Neglecting minor losses, one more thing is given, that you don't have to take the minor losses. The ratio of the frictional pressure drop in pipe 1 to that in pipe 2, delta P1 by delta P2 is given by. Okay, so you have been given the friction factor for the turbulent flow, the relation of the friction factor for the turbulent flow. So by this frictional head loss FLV square by 2GD, can I apply this in turbulent flow also? Yes, this is valid for laminar as well as turbulent flow. Okay, what changes is the F value. For laminar we know that the Darcy's friction factor is 64 by Re, whereas in this turbulent case it is given. The relation given is K into Reynolds number raised to power minus N. Okay, so let's substitute the relation, that is K Reynolds number raised to power minus N L V square by 2GD. Okay, K Reynolds number is rho Vd by mu raised to power minus N L V square by 2GD. Rest is the calculation part, but many of the students will commit error while solving this question. This is a pretty simple question, but what makes this question tough is its calculation portion. Okay, again let's simplify it further. That implies this will be K rho by mu raised to power n V raised to power minus n L V square D raised to power minus n upon 2GD. Simple mathematics. I have taken this this and this value out of this bracket, V and D value out of this bracket. Let's further simplify this. So that will be, this is constant, this part is also constant, 2G is constant, L for both the pipes is same, so let this be constant 2. Okay, so can I substitute all these constants with a new constant, that is K1, and this is V raised to power minus n and V square, this becomes V raised to power 2 minus n, and we have a D in the denominator and D raised to power minus n in the numerator, so this will be D raised to power minus n minus 1. Okay, so finally I have reduced this frictional head loss in this form. Okay, now see the options. The options are only given in the form of D, that is D2 and D1. So we have to convert this velocity also in the form of D. How can we do that? We can use Q is equal to AV. Okay, so V is Q by area and area is pi by 4 D square. Okay, so for first pipe it will be D1 and for second pipe it will be D2. Let's substitute this here. Okay, what we get, that implies HF will be K1 Q by pi by 4 D square 2 raised to power minus n D minus n minus 1. Okay, so can I say that Q is also constant? Constant means that it is same for both the pipes because it is in series. So whatever the mass flow rate, the flow rate will be passing through first pipe, the same flow rate will be passing through second pipe. When I will take the ratio, this will get cancel out. So that is why I am taking it as a constant. Okay, so this further reduces to K1 D raised to power 4 minus 2n into D raised to power minus n minus 1. This is, let's write here. Okay, which is further equal to K1 D raised to power minus n minus 1 minus 4 minus 2n. I'm just solving it. Okay, K1 D minus n minus 1 minus 4 plus 2n. Okay, and that implies finally HF is equal to K1 d raised to power minus 5 plus n. Okay, so this is the relation between the frictional head loss and the diameter. Okay, so if I multiply rho g on both the sides, can I say that I will get pressure drop? Yes, because hf is equal to delta p by rho g. So if I multiply hf into rho g on both the sides, that will give me pressure loss. Okay, let me rub some portion. I mean, okay, so now delta p1 will be k1 d1 minus 5 plus n. Similarly, delta p2 will be k2 d2 minus 5 plus n. Nice. And we have to find delta p1 by delta t2. Delta p1 by delta p2 is equal to, oh sorry, this is k1 only. I mean, this is constant. This will get cancelled out. So d1 by d2, I mean raised to power minus 5 plus n minus 5 plus n. Okay, check the options. This is raised to power 5, this is 3 raised to power minus n, 5 plus n, this is 5 minus n. But here this is d2 by d1 raised to power 5 minus n, and we are getting d1 by d2 raised to power minus 5 plus n. So let's interchange this. I mean, this is equal to 5 minus n. So this will be our answer, option A. Okay, thank you.